So before drawing Penrose-Carter diagram, we have to recall a few points, a few properties of the Schwarzschild metric that we have discussed during the previous lecture. So we have ended up writing one of the final formulas that we have been using during the previous lecture has the following form. So we have rewritten Schwarzschild metric in this form, dt squared minus dr star squared minus r squared d omega squared, where r star is a tortoise coordinate, which is equal to r plus rg log r divided by rg minus 1. And it is important that these r and t coordinates do not cover entire space-time. They are valid only for r greater than rg. So they are similar in this spirit. They are similar to Rindler coordinates that have been discussed during the first lecture and which cover only some part of the entire Minkowski space-time. So to draw the Penrose-Carter diagram honestly, to do that honestly, one has to find such coordinates which cover this space-time entirely. And how one does that? One should embed this space-time in a flat. Well, one of the ways to do that is to embed such a space-time, four-dimensional space-time, into a big enough flat space-time as some hyperplane. So we basically consider some big enough Minkowski space-time, which has bigger than 4 dimensions, and embed this thing as a hyperplane into some sort of hyperplane which is curved, and then find some coordinate system which covers this space-time entirely. Well, there is a mathematical theorem stating that with the use of map which map has appropriate mathematical properties, any four-dimensional space-time can be mapped into a flat 10-dimensional space. Intuitively, this theorem can be understood on general grounds. So 4x4 matrix, symmetric 4x4 matrix, which is G mu, has 4 plus 1 over 2, so 10 parameters. But we can use general covariance, which is 4 functions. With the use of the 4 functions, we can fix 4 of those. So that reduces the number of parameters to 6. So every 4-dimensional metric basically has 6 parameters. So to fix these 6 parameters, one needs 6 extra dimensions. That is the reason the embedding can be done into 10-dimensional space-time. But so we are not going to go in greater detail in this theorem. Also, we in our concise course on general relativity will not describe this kind of embedding in greater detail. But you will have to believe me that the coordinates that I'm going to derive right now, which are called Kruskal-Szekeres coordinates, after those who have invented them. So I'm going to propose a way to derive, well, a standard way to derive Kruskal-Szekeres coordinates, which is not using embedding. But I will just declare that these coordinates cover the Schwarzschild space-time entirely. And you basically have to believe me, because I'm not in a position to prove it rigorously. So how do we do that? We want to get rid of the singularity of this metric at r. So this metric is singular at r equals to rg. We want to get rid of this. How do we do that? We use the following coordinates. We propose coordinates light coordinates. So u and v. U, which is so we propose u t minus r star, v t plus r star. After this change, after such a change of the coordinates, this metric can be represented as 1 minus rg divided by r, which is function of u and v, times du dv, minus r squared, which is a function of u and v, d omega squared. And so here, r is basically understood as some implicit function of u and v, and the form of this function is fixed by this and this relation, because from here we can find r star, which is equal to 1/2 v minus u. And basically I rewrite this expression like this, and this is a function of u and v given by this relation log r u and v minus rg minus 1. So this is a relation specifying this function. So the singularity of this metric, which appears again when this guy goes to rg, when this guy goes to rg, this goes to minus infinity, so the singularity is basically moved to minus infinity. So, but let us see what happens as we approach this point in terms of these coordinates. One can see from this formula that this term is limited as we approach rg, but this becomes huge. So approximately we can drop this term off and keep only this. So then in this limit, in this approximation, we can write that 1 minus rg divided by r is approximately equal to v minus u divided by 2rg. So this is the approximation. And now we can use this here. So in the vicinity of this point, we have that the metric is approximated by like this. It is exponent of v minus u divided by 2rg du dv minus rg squared d omega squared. And this is equal to exponent of u minus u to rg du exponent of v to rg dv. This is just a rewriting of this metric, minus rg d omega squared. Remember that we are around the point when r approximately equal to rg. So now one can make the following change of the coordinates. One can use new coordinates, u, which is equal to minus 2 rg times exponent of u divided by rg, and v, big V, which is 2rg times exponent of v divided by 2rg. So using these coordinates, this metric can be represented as follows: dv du minus rg squared d omega squared. So amazingly enough, in this new coordinate, this part becomes flat in the vicinity of the point r goes to rg, and not singular. And so that is the goal of the transformations that we have been making. So let us make this transformation from the very beginning. So if in this metric, ds squared 1 minus rg divided by r dt squared minus dr star squared minus r squared d omega squared. From the very beginning, we have made the following coordinate change. So that's what we basically found. Minus 2 rg exponent minus t minus r star, which is u, divided by 2rg, and v equal to 2rg exponent of t plus r star divided by 2rg, which is, this is v, just to remind you, so this is u, this is v. So in original coordinates, this transformation would look, in original r coordinates instead of r star, this coordinate transformation would look like this, minus t minus r divided by 2rg multiplied by r divided by rg minus 1 half. And this would be 2rg times exponent t plus r divided by 2rg, r divided by rg minus 1. This expression I have obtained just by putting into the here and here the expression for r star through r. So then one would get this. So if one would make this transformation in this metric, one would obtain the metric in this form. ds squared is equal rg divided by r u, which is a implicit function of u and v, times exponent of minus implicit function of r, implicit function r of u and v divided by rg times d u times d v minus r squared u and v times d omega squared, where this function can be found from here, from these expressions. This function is easy to see to be equal to, so if we just multiply this to this, one will get rid of t, and then the function r of u and v divided by rg minus 1 multiplied by, so this is implicit expression, this is expression defining this implicit function of u, r, u, and v divided by rg is equal to minus u times v divided by 2rg squared. So this metric is called black hole metric in Kruskal-Szekeres coordinates. U and V are Kruskal-Szekeres coordinates. And this metric is regular. When R goes to Rg, this term is regular, and everything is perfectly good, etc., etc. So this metric doesn't have singularity, and moreover, as I promised, well, without explanation, this metric covers entire black hole space-time. So in these coordinates now we can do a conformal map to the Penrose-Carter diagram of the black hole.